Well, good morning. This is 11:36. We're 6 minutes late getting started, but I had to run down to the office for something and it took a little longer than I thought it would. But this is linear algebra, math 237. It's supposed to be meeting at 11:30, but right now I'm the only one in the room, so hopefully some students will be showing up in a bit. I would make some announcements now, but nobody's in the room to hear them. And I'll wait till someone comes in before I make those. I'll try to remember to make them then. No roll to call, so let's pick up where we left off last time. Last time I had some people here. This time I don't, so I think my mark is that we're in Chapter 2, matrices, 2.4 elementary matrices, and on page 80, the very last part of example 6. And I can't say for certain why I put the mark here. I guess we had gotten down to the point of determining the two elementary matrices that we think that if we multiply together, we should get the matrix A we had at the very beginning. It doesn't look like that's the case, though. No, I'm sorry, that's not what we're doing. Okay, I'm trying to recall what we did here. Okay, we're forming an upper triangular matrix by doing getting the matrix in row echelon form. We did that by two elementary matrices, 1 and 2, and then we did the inverse of those matrices in reverse order, 2 and 1. And when we did that, that gave us the lower triangular matrix. So that's what we were doing. We did the two uppers, identifying the two elementary matrices that got us to an upper triangular matrix, and they were E1 and 2. At the same time, we were tracking and keeping up with what was E inverse, E1 inverse, and E2 inverse. You multiply them together in the other order, E1 first and then E2. Let me get my pen set up. Okay. All right, there. Okay. So here was our E1 inverse was this matrix, 1, 0, 0, which of course 0, 1, 0, and 2, 0, 1. Okay. Now, just looking at that, you see it's already a lower triangular matrix. Okay. E2 inverse, okay, we found out to be 1, 0, 0, 0, 1, 0, 0, negative 4, 1. Okay, both of those elementary matrices, and both of them happen to be lower triangular matrices. Okay? Multiply those two together, and what do you get? Well, you're going to get a 3 by 3 matrix, of course, and it's going to be 1, 2, 3, 1, 2, 3, 1, 2, 3. So the 1, 1 entry is going to be first row, first column in this order. 1, 0, 0, that's a 1. First row, second column, 0, 0, 0. and first row, third column, first row by third column, 0, 0, 0. Then do the 2-1 entry here, will be second row, first column, 0, 0, 0. 2-2 entry is second row, second column, which would be 0, 1, 0. And the 2-3 entry, second row, third column, 0, 0, 0. Okay? Now, third row, first column, 3-1 entry, 2, 0, 0, so 2. Third row, second column, 3-2 entry, 0, 0, negative 4. And then the 3-3 entry, third row, third column, 0, 0, 1. Okay, so that gives us then your L matrix, which is the lower triangular matrix made up of the product of your inverse matrices of the two elementary matrices that created your upper triangular matrix, okay? So, sort of like you're running around in circles here and get a little dizzy. Let's see if those two then form your A. The lower triangular matrix we began with, we got from our first two steps, the reduction, the row echelon to row echelon form. The upper triangle is LU, remember that. So you do the L first, which is this one, 1, 0, 0, 0, 1, 0, 2, minus 4, 1, because it's LU matrix, the LU matrix, okay, remember that, okay, times the upper triangle matrix, which we got last time by our elementary row operations, got it into this form, 1, negative 3, 0, 0, 1, 3, and 0, 0, 14. Okay, let's see what happens if we multiply those two together. 3 by 3 by 3 by 3 is going to be a 3 by 3. Okay, the 1-1 entry is first row, first column, 1, 0, 0, that's a 1. First row, second column, negative 3, 0, 0, that's a negative 3. First row, third column, 0, 0, 0. Okay? 2-1 entry is second row, first column, 0, 0, 0. 2-2, second row, second column, 0, 1, 0. And 2-3 entry, second row, third column, 0, 3, 0. Okay? Now, 3-1 entry, third row, first column, 2, 0, 0. So 2. Second row, second column, third row, second column, 3-2 entry is be a minus 6, minus 4, that's minus 10, 0. Minus 10. And then the 3-3 entry, which is third row, third column, 0, minus 12, plus 14 is a 2. Let's see, is that the A we started with? The A we started with was 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2. Exactly. So, we do now know how to, in some sense, factor an invertible matrix. It has to be an invertible matrix, meaning it has to be square, but not all squares are invertible, but it's got to be square, and if it is invertible, a non-singular matrix, if it is invertible, if it does have an inverse, then you can break it into its lower triangular times the upper triangular. How do we get that? We started with the matrix we started with, and then you do the elementary row operations to get it into your upper triangular matrix, okay, into Gauss elimination. You do that. While you do it, you identify the elementary matrices that do those steps, okay? While you're doing that, go on and figure out the inverse elementary matrices that do those steps, and number of them, E1, E2, E3, and E1 inverse, E2 inverse, E3 inverse, until you get to your upper triangular matrix, okay? When you get there, stop, okay? And just as a note here, you do not have to get that last diagonal entry to be a 1. I think probably in Gauss-Jordan we did, because upper row echelon form requires the diagonal, well, the first non-zero entry in each row to be a 1. That's where you stop short. You just, once you get the upper triangular matrix, whether it's completely row reduced or not, once you get it, stop. Okay. Now, take those inverse elementary matrices in the reverse order, in other words, starting, if you think of it starting from the right and then adding them to the left, that reverse that, not adding, so to speak, multiplying to the left. The reverse of that would then be start the E1 inverse on the left and multiply by E2 inverse, E3, as many as it took to get your result. And when you multiply those together, and by the way, all those inverse matrices are going to be upper or lower triangular. When you multiply them all together, that gives you a lower triangular matrix. That's going to be the lower triangular matrix. When you multiply them all together, that is your L, and then your U you got from the row reduction to begin with, and you multiply those two together and you get the original matrix, if it is an invertible matrix. Okay. Now, why did we go to the bother of doing that? Well, once you have obtained the LU factorization of a matrix A, you can then solve the system of n linear equations in n variables, AX equal B, very efficiently in 2 steps. Okay? And let's see, I guess I can write the steps here. We got plenty of room. So here's what you got. You got matrix A times unknown variable vector X is equal to given vector, constant vector B. Okay? And you want to know your solutions for that. Okay? And it says this is very efficient in 2 steps. Okay. First step. Write a new vector Y to be your upper triangular matrix that you have gathered before. That would be it in this case. Okay, upper triangular matrix times your matrix, your vector X. Okay, that's going to be, in this case, it happened to have been a 3 by 3 by 3 by 1, and that will give you a 3 by 1, and that's going to be your Y vector. Now, Y has nothing to do with the problem yet. It's just sort of an intermediate thing to do. So that's the first thing you do. Okay? And in that same step, this is what gets me about this, they say 2 simple steps, but then the steps have multiple pieces. Here's the next part. In the first step, then solve this for Y. Okay? You just found out what the Y is. Okay? And then you multiply it by the L times Y. Okay? Equal B. Okay? Because if you think about it, A is LU. I can't write. Let me see if I can clean that up just a little bit. Okay. A is LU, so LUX equal B. That's our original, that's what we're trying to solve. And if you let Y equal UX, this part right here is your Y vector, and then multiply that by L, Ly is equal to B, and solve that for Y. Okay. Okay. Now, that's the first step. Second step. These, to me, are not intuitively obvious. Solve UX, okay, equal Y for X. Okay, now, you see that initial thing, Y is equal to UX. You don't really do anything with that. You just say that's what it is. Okay? Then you multiply that by L on the left, and Ly is equal to B. You already knew what B was. And solve that for Y. Yeah. And then you have that UX is equal to Y. Solve that for X, and you've got it. The column matrix X is a solution of the original system because of all this. AX is equal to LUX, which I said, which is equal to LY because Y was UX, and that's equal to B because AX equal to B. The second step is just back substitution, okay? Because the matrix U is the upper triangular. The first step is similar, except that it starts at the bottom of the matrix because L is the lower triangular. For this reason, the first step is called the forward substitution. Second step, back substitution. Okay. A lot of blah, blah, blah when you're just using words and letters and things like this. Let's actually do one. Hopefully it'll make a little more sense. Okay? So let's erase all that and solve this system of equations. X1 minus 3x2 is equal to negative 5. X2 plus 3x3 is equal to negative 1. 2x1 minus 10x2 plus 2x3 is equal to negative 20. Okay. All right. Now, okay, hold on just a minute. My head is really clogged up. I think it must be pollens. I found out yesterday, anytime I went by an open window, I started sneezing. And I didn't think I used to have hay fever, whatever you call it. But I must be getting it in my old age because it just seemed like it never stopped. And then earlier today, in the the previous class, actually in both classes, I had sneezing fits in both classes. And I'm not sure, it's when someone came in from outside and they must have been bringing some pollen in with them. I just started sneezing like crazy. So my head is really clogged up. That may be, if I'm sounding sort of like I'm talking from the middle of a drum, that's why. Okay, so sorry about that. But it's hard to stay focused because I keep feeling like I'm going to start sneezing again. Okay, so first thing let's do, let's write the the coefficient matrix. Okay, I think I'll write it over here. So matrix A is going to be 1, -3, 0, 0, 1, 3, and 2, -10, 2. Okay. The variable matrix, unknown matrix, is x1, x2, x3, and that's equal to the constant matrix, or vector, if you want to call it that, -5, -1, -20. Okay, so that's your A, X equal B. Okay. Now, I think I am going to have to pause and run down the hall and clear my head because I'm having some drainage problems. So hold on just a bit. I'll be right. All right. Sorry about that. I can breathe a little more easily now, but still not totally cleared, but at least it's better. All right. Now, we wrote the system of equations as the matrix equation there. Okay. Now, thing to note, that A is the same A that we used in example 6. We've already determined the LU factorization of it, so we don't have to go back and redo that. Okay, so let's just use the LU factorization that we had. This will be, the L, remember, was 1, 0, 0, 0, 1, 0, 2, -4, 1. Okay. The U, the one we got first, was 1, -3, 0, 0, 1, 3, and 0, 0, 14. Okay, and remember we've already shown that's equal to A. Okay, so that product is equal to times x1, x2, x3 is supposed to equal -5, -1, -20. Okay, written a little sloppily, but there. Okay. Now, what it said to do first, if you notice step 1, write y is equal to ux. Okay, now reminding ourselves, this is L and that's the U. Lower triangular, upper triangular. Okay, so we write, and let's see, get it on the right side, the correct side, Ly, let y equal ux. Okay, so your y here is ux, this thing right here. 1, -3, 0, 0, 1, 3, 0, 0, 14 times x1, x2, x3. Okay, now there's not much you can do with that. You could write it as a series of equations, but I mean, you just write it. That's what it is. That's your y vector. Okay, now what you want to do is solve Ly is equal to B. Okay? And this is not using this y per se, but it is that same y, but we're just not going to write it in that way. We're just going to write it this way. The lower triangular matrix, which is 1, 0, 0, 0, 1, 0, 2, -4, 1, times your y vector, which is y1, y2, and y3. Okay, we couldn't get those out of this. No, not yet. Okay, and we say that's equal to our vector b, because this is lower triangular times this y. Okay, is equal to b, which was -5, -1, minus 20. Okay. Now, because this is a lower triangular matrix, the L is here. This is L. Remember, that's our L here. You can figure out what Y1, Y2, and Y3 are right there. In fact, Y1 is pretty obvious. 1 times Y1 is equal to Y5. And, I mean, you can do the other two, plus 0, plus 0. So basically, this is what they call the forward substitution. Y1 is equal to negative 5. Okay? With that in place, then it just happens to be, the next line happens to be 0, 1, 0. So this tells you that Y2 is equal to negative 1. Okay? And then, knowing those two, you can write down the third equation that 2 times Y1, which is minus 5, minus 4 times Y2, but Y2 is minus 1, plus Y3, what, yeah, not cubed 3, Y sub 3. Okay, it's actually looking ahead to the next step. So basically what you've done is a matrix multiplication here. 2 times Y1, but you knew Y1, minus 5, minus 4 times Y2, which was a minus 1, plus 1 times Y3, okay, is equal to that third row, first column, only column, gives you your 3, 1 entry. This is equal to negative 20. Okay? Now, cleaning that up a little bit, negative 10 plus 4 plus Y1, Y3 is equal to negative 20. Okay? Minus 10 plus 4 is minus 6. Add 6 to both sides, and you get Y3 is equal to minus 14. Okay. So now we got our Y2, Y1, Y3. Okay. Now, we can write that down here, which is negative 5, negative 1, negative 14. Okay. Now we do your back substitution. 14, oh my goodness, is this a student coming? Oh, well, one who's never in. Okay. Okay.
You said the one that's never in?
Yes.
You mean the one that's always in?
Now, what was that? Oh, okay. I got blessed. Okay. Let me find the right page and everything else. Muhammad is here today. Okay.
Always in.
Yes. And close to on time, too, right? Not quite, but close. Okay. All right, let me turn on the projector. Okay. I hadn't even gotten out my watch yet because no one was here I needed to keep time for it. Okay, and we go to 11:45, and that's just a little over 30 minutes from now. Okay. So, as soon as this comes up, I'm doing example 7 on page 81. This is in chapter 2, matrices, 2.4, elementary matrices. We're doing this roundabout way of solving the matrix, okay, a system of equations. So here we have a system of equations.
Here. That we use in triangle, lower triangle and upper triangle matrix.
That's exactly it, okay, which is more involved than just doing Gaussian elimination, or even just row reduction. That's the quickest.
Gaussian and those and these will still give you the same result, right?
Yeah, exactly. There is some reason for doing this. They say, and I think it has to do with this is fairly easily programmed, okay? Especially for huge matrices. Now, it doesn't seem to me it would be, but perhaps it is. So we've got the system of equations here. We wrote the coefficient matrix times the variable matrix equal the constant matrix, or vector. This matrix is a column vector, column matrix. Okay? Now, last time we had split this A, it's the same A as we had in the previous example, into a lower triangle and upper triangle matrix. So I didn't go back and redo that. We just used the result we got before. Okay. And that is multiplied by your x1, x2, x3 to give you that. Okay, I just split this into the factorization. Now, this technique says the first thing you do, and this is a little out of order here, is come up with a new vector y. Okay, column vector y, and let's say that's ux. That's this part right here. Y is equal to this. So it's 1 minus 3, 0. 0, 1, this u times x. That's your y. And that times this is that. No, wait. No, sorry. No, it's from this. I don't know why I wrote that down. I think I was just copying. No. Sorry. That came later. Forget this column right here now. We just wrote that y is equal to this times that. Okay. Forget this for now. Okay. Now, then that tells you that L times y is equal to that, because this is your y right here. So L times that y. Okay. Now we don't know what y is. We know it's that, but we don't know what it is. So let's just name it y1, y2, y3. Okay? So L times this is equal to that. Okay? This is easy to solve. It's what they call forward substitution. Because you see here, this entry here, if you multiply these together, it'd be y1 plus 0 is equal to minus 5. That says y1 is equal to minus 5. Okay? Then the next row just happened to have a 0 here too. That made it easy, but it didn't have to. But if you know what y1 is, it'd still be easy to do. But this one is even easier. 0 plus y2 plus 0 is equal to minus 1. So y2 is equal to minus 1. You got two of them, just like that. Now, the third row is not going to be quite as simple, but it's still pretty simple. 2y1, which you know to be minus 5, minus 4y2, which you know to be minus 1, plus y3 is equal to minus 20. Okay, so just do the math there. This will be minus 10 plus 4 plus y3, that's a 3 there, it's ugly, is equal to minus 20. This is minus 6. Add 6 to both sides, you get y3 is equal to minus 14. So there's your y.
I see the 10 and the I thought it was like y1.
y1 is minus 5.
Is minus 5, so that's times 2 would give you negative 10.
Yes.
But we have
y2
is negative 1.
Right. So minus 4.
That would give you a positive.
Positive 4.
Positive 4. That would set you back into negative 6.
Okay. Yeah, and that became negative 6.
So what do you get negative 20?
Okay, but wait. And the third element here, you see you're doing your matrix multiplication. 2 times y1 minus 4 times y2 plus y3 is equal to minus 20. Okay? So you did this one. That was minus 10. Plus this one, which is plus 6.
It gave you minus 6.
Plus 4, I'm sorry. Plus 4. Plus y3 is equal to minus 20. You see that these combine to be that. The row 3 times column 1 is equal to 3 1 entry here, minus 20.
Is the arithmetic that doesn't, I'm not seeing the minus 20 because I'm seeing like, you know, the 2 times negative 5 give you 10. Give you negative 10.
Right.
And negative 2, negative 1 give you, negative 4, negative 1 give you 4.
Plus 4.
So plus 4 minus 10 give you.
Wait. Okay.
Minus 6.
Minus 6. Okay. Minus 6 plus y3. So you do this is equal to that. It's matrix multiplication. Okay. All right. This one is this times this. This plus this plus this equal that. Well, that's just going to be y1 equal negative 5. Okay. Then it's this plus this plus this is equal to negative 1. Well, the only one to give you anything is y2 is negative 1. And then the third one is this. The product of these plus the product of those plus the product of these is equal to the third. Minus 20. Just an equation that came from your matrix multiplication.
Now I see.
Yeah. See, this is your unknown. This is known. That's known.
Okay, what was confusing me, I was assuming the negative 20 came out of the factorization. It wasn't known from the beginning.
It was known from the very beginning.
That's what that's why I was like, how you got negative 20? It's like, well, negative 20 was known. It's not from the arithmetic. I was like, negative 10 and 4 doesn't give you 20. So that's why I got me.
Yeah, you still have this 1 times this plus this is equal to negative 20.
Yeah.
Okay, and then you solve for y3 to get negative 14. So now you take this thing, this is your y, y1, y2, y3. That's what this is. So you set that equal to this. It just happens out of the first two entries the same, negative 5, negative 1, and then y3 is negative 14. Well, now you have another real simple matrix multiplication to do, but now you do back substitution. 14 times x3 is equal to minus 14. Guess what x3 is? This is where I was when you came in. x3 is equal to? No. Look at this. Okay. 0 plus 0 plus 14x3
Oh, 14 equals to negative 14.
is equal, 14x3 is equal to negative 14. What's x3? Negative 1. Yeah, right?
What is the negative 1?
Oh, I thought you said it. Sorry. Okay. Just taking the third equation here. 0 plus 0 plus 14x3 is equal to negative 14. See, the 3, 1 entry will be the third row times first column will be the 3, 1 entry.
Okay, the left side will be 14.
14x3. That's right.
Oh, okay. Now it's divided. Okay.
Yeah.
I thought it was,
14x3 is equal to minus 14. And then you divide both sides by 14. So x3 is equal to minus 1. Okay? Then the next equation here says 0 plus x2 plus 3x3. Well, 3 times minus 1 is minus 3, right? Is equal to minus 1, right? So x2 is equal to 2. Is that what you said? Yeah. x2 is equal to 2. Okay? Now the first equation would give you that x1, 1 times x1 is x1, minus 3 times x2, but x2 was 2, so that's minus 6, right? Plus 0 is equal to minus 5. So what's your x1? One. There it is. 1, 2, negative 3. There's your solution. Not mean 1, 2, negative 1. That's your solution. Okay? And sure enough, that's it. All right. Now, seems like a lot to go through to get something that if you had just done your, what you call it to begin with, your augmented matrix, you'd have had it done a long time ago. You get the same answer, okay? But this gives a way that if you can train your computer to do your LU matrix, which is doable. I mean, we did it last time. We had that last step to go today, and I did that first of the period. Nobody was in here, and we came up with the U. We had already gotten the L, but we'd already gotten the U, got up with the L, okay? And that's where we left off last time, multiplying those two inverse elementary matrices together to give us the L. We got it. And then we verified the LU was equal to A. We did that. And we meaning me, okay, because no one else was in here. And then we got into this thing, okay? It was beginning at 11:30. See this?
Earlier today.
Yeah, today.
Oh, okay.
Yeah. See, the class started at 11:30 or 11:36, I think it was, before I got started. And then we and got to here now. But the process of getting this was really the same process as row elimination up here, which you're doing it. Why stop there? Just get your solution. I mean, you could have done that right then by doing that first step, okay? But you would have been doing the same operation to your other part, but we didn't, okay? So they split it into this, and those are all, I'm going to say, programmable steps to get this, and then to reverse that, and every time you do a step here, you identify the elementary matrix that does that same thing, and you identify its inverse of that elementary matrix, which is the easy thing, and then once you've got those, you multiply them together to give you the L. And that's where we left off last time, that's what we did first. So that gave you your lower identity, lower triangular matrix. And then what you do is then go to this step. Once you split your A up like that, start by saying the Y is equal to the upper times the X. Okay? Just leave that like that. That's what it's equal to. Then figure out what the Y is by the lower times the Y is equal to the constants. And that's what we just did here. And that's by forward substitution, because you start up here and work your way down. Okay? And you get what the Y1, Y2, and Y3 are. And once you got that, plug that in here, because that's what Y is this thing. And then you do your back substitution and start from here and work your way up. And that'll get your answer. It's a kludgy, backward way of doing it, but it certainly works. But as far as I know, all these steps are fairly easily programmable. Okay? And that must be why they do it. Okay. So we've gotten the X. 1, 2, -1. That finishes 2.4. Homework exercises here would include any of the odds 1 through 7, and they're all at calcchat.com. 9 or 11 or both, they're at calcchat.com. 13 or 15, they're at calcchat. Any of the odds 17 to 21, they're at calcchat. Any of the odds 23 to 25 or both, they're at calcchat. And here's Daniel. I'm putting y'all in the right class this time. Last Thursday, I had already marked this class for a different class because the people who were here were in my 27 class too, and I just marked them on the wrong page. But that's over with now. Okay, where did I leave off? 23 or 25 or both. They're at CalcChat. Any of the odds 27 are doing the homework exercises for 2.4 on pages 82, 83, and following. Okay? Any of the odds 27 to 33, they're at CalcChat. 35 is a true-false. That's at CalcChat. 37 is a writing problem. You can look at that, think about it if you want to. 39 should be at CalcChat. Either 41 or 43 or both, they should be at CalcChat. 45 or 40, no, 45 should be at Calc Chat. 47 is a writing problem. You can look at that if you want to. That's at Calc, should be at Calc Chat. I don't know what they'll do there. Now, here's one of these other places that kind of gripes me, because here they're coming up with another definition. Didn't give it in the text, but giving it in the homework problems. And I don't even know how to pronounce this one. Okay? Idempotent. I-D-E-M-P-O-T-E-N-T. Let me clear this out of the way so I can write this down. It's in the problem set. And why they didn't, if it was important, why didn't they do it in the text? Okay. I-D-E-M-P-O-T-E-N-T. Idempotent. I don't know how you pronounce it. Okay. Yeah. Yeah. So whatever this is, it determines whether it is. And here's the definition. An idempotent matrix, number one, has to be square. Okay, not surprising. Okay. It's idempotent if a squared is equal to a. Okay. Why that's important, I don't know. But if a matrix multiplied by itself gives you that matrix, it's idempotent. And questions 49 and 51. Okay. 49 and 51 are basically saying determine whether these two matrices are idempotent, or however you pronounce that. So you just do it, see if that happens. 53 is coming up with two values A and B to make A idempotent. So you can play with that if you want to. There's a guided proof on 54 which continues the process of idempotent, but they're not in the back of the book, so I'm not assigning them. 55 is a proof dealing with idempotent, or however you say that, matrices. 57's a proof also, but it doesn't seem to be dealing with idempotent matrices. 59 is a proof.
Is it IDE or IDO?
I-D-E-M-P-O-T-E-N-T. I-D-E-M-P-O-T-E-N-T. Okay. It's what? Idempotent.
Yes.
Okay. Idempotent. Okay. Fine. Okay. 57 is a guided proof, but that doesn't seem to have anything to do with idempotent matrices. 59's a proof, and it doesn't seem to have to do with those either. All right. Was that someone at the door? Had to have been, but I don't know who it was. Okay. That finishes 2.4. So let's move on to 2.5. Okay, so I'm going to clear the screen even though there's not much on there. This is applications of matrix operations. Now, here they do put in the text what they're talking about here. Stochastic matrices. Now, I don't know if you'll ever use these, but a matrix that, all right, let's talk about probability just for a moment. I know that's not this course, but matrices are used in that. If you have a situation and you have n possible outcomes, okay, then the probability of any one of those outcomes will be some number, but it's going to be something less than possibly equal to 1, but it can't ever be more than 1, because a situation is either going to happen or it's not going to happen, but it can't happen more than once, okay?
Is class almost over?
Pardon me?
Is this class almost over?
Is what?
Is this class almost over? No.
We'll be over in about a little over 10 minutes.
Okay, can I just wait here for 10 minutes?
Pardon me? Oh, sure. Yeah,
I
you're
got
welcome.
you.
Okay. So probability, whatever the events are, the probability of it happening can't be more than 1. Because one would guarantee it's going to happen, and none of the other events are going to happen. So if you have a whole group of probabilities that all are possible, then the sum of those is equal to 1, if you've got them all. Now, if you don't know if you got them all, it's going to be less than or equal to 1. Okay. So, now, this is, and stochastic mean, the term stochastic means regarding conjecture. That is, an n by n matrix P is a stochastic matrix when each entry is a number between 0 and 1 inclusive, and the sum of the entries in each column or row, I guess it's column, is 1. That means if you got all the possibilities there, the sum of the probabilities of those things would be 1, because the event has to happen, but we don't know what each one. So I don't know if any of you are going to go into probability theory, if you're going to be dealing with something that has it. That's the first example here. Since I don't know that any of you will deal with that, what are your majors anyway? Electrical engineering, and you're both of you electrical. Maybe electrical do stochastic things. I could conceive that you could, but if you do, I'm sure they're going to teach it to you. Okay? Another one is a consumer preference model, or this is a consumer preference model, which is stochastic, because if you have consumers, they're going to have a preference for one product over another product, right? But they're only going to, the sum of those has to be 1, if you have a bunch of different consumers. So there's an example. So I can see this more in industrial engineering than I can electrical, but maybe you could use it in electrical. Okay? Example 3 is also a consumer preference model. So I don't see what, now, any of you going into cryptology? I don't think so. Okay? So that uses matrices. Okay? And I'll let you read through any of that you find interesting. Okay? And you can encode messages and decode messages using these matrices. Okay. Now here's the one that just about every one of these books like this love to do, is the Leontief input-output models. Okay. And they love to do them, and it's maybe has some practicality, but again, I think of it more of something for industrial engineering than the other fields. So unless you really want to do some of these, I say let's just go past them. All right? Now, don't think y'all get with this either, least squares regression analysis. This is, again, in statistics. You might do this for a fair amount of time, but it's not going to be all that common. That uses matrices, okay? And the definitions and descriptions are all here, and then it's finding the least square regression lines. And frankly, I don't see why spend a lot of time on this section at all. These are all examples of things coming from other viewpoints. So I'm all in favor of skipping that whole section, which means we just finished chapter 2. Unless you have a question about some of those. Stochastic models, least squares fits, Leontief, and what was the other one? Oh, cryptography. that kind of stuff. I just don't see taking lots and lots of time to go some of that stuff that I know that I've never used it except for teaching it, okay, ever. Now, when I did teach statistics, we used some of those principles, but I still never did the matrices with it, okay? That was beyond what the statistics students could use. So unless you know you're going into that, that's all I want to do with that. So I have test 2 ready, which is chapter 4. So y'all ready to get it? Okay. I say I have it ready. Yeah, here it is. I have several different versions out there, but this is the one. Huh? You are? Oh, okay. Sure you can handle both of them? All right, good deal. All right, so there's your test 2, which sort of leads me to the logical observation that I only have one research paper in from the whole class. Neither of you have done that one. And I only have one test in from the whole class, and neither of you have done that one, okay? So I've just given you test 2, and I don't have either a research paper or test 1. Oh, and here was the announcement I meant to make at the beginning of class, but no students were in here. There's actually 2 of them. Let me do this one first. It's already over with, this part, but the building isn't. They have just completed on the Birmingham West campus a brand new building called the Academic Success Center. I've not been in it yet. It's a very impressive looking building from the outside. I talked with someone who had been on the inside. He said it was amazing inside. Huge. Lots of space in there. I'm just not sure what they're going to do in there, but they got lots of space to do it. Okay?
They got FAFSA in there.
They got what?
They had Birmingham FAFSA in there.
Birmingham what?
They moved their financial aid building.
Yeah. Oh, yeah, for sure. Most of the student services stuff is going to be in this building.
Bookstores in there.
The what?
Bookstores in there.
Oh, there's a bookstore move too.
There's a bookstore in there. I think they're going to build a cafeteria in there.
Oh, yeah, they're going to be. They don't have the cafeterias finished yet? Oh, okay.
Everything just started.
Okay.
Yeah. I mean, there's a lot of stuff that's going to be upstairs too.
Right.
Big 2-story.
Yeah. Huge thing. Now, I understand there may be 2 classrooms in the building, which would be fantastic if there are, because we haven't had a new classroom anywhere in a very long time except the ACAT building, and those are all computer classrooms, and we can't use them for anything. But that department got some new classrooms, but nobody else did. So the grand opening was today, ribbon cutting, that kind of stuff. That was this morning. So anytime after today, if you're by the Birmingham campus, you want to go in, you probably can get someone to show you around the building. It should, from what you say, it's pretty impressive. Okay? Second?
What campus is that?
It's on the Birmingham West campus, but it's right on the border of the East campus. You know, Wilson Road, it separates East and West campus. Well, was it middle or elementary? It's one of the Winona schools. They tore it down and built this in its place. And they sort of deeded that land over to us. So we've got it now. Right on Wilson Road. Across Wilson Road on the East campus, then is the new Resident Hall number 2. It's right next door to Residence Hall number 1. Okay? So that's open too. I don't know if anyone wants to go in there unless you're going to be living there. But if you did want to go see it, maybe you can get someone to show you that around.
That is open now? They finished it?
They finished, I guess it's finished because they had the ribbon cutting and official openings today, but nobody's in there yet. Yeah, the dorm too.
Okay.
Have you been in it?
No,
the new dorm?
It's not open.
Huh?
It's not open, not that I know.
No, it's not open for business, but they supposedly have finished the building today. Okay. Or the grand opening was today. I don't know if they'll start taking students this summer or not, but probably next fall. So that was one announcement, okay? The second announcement is this, and this may have more appropriateness to you. It's a good news, bad news situation. The good news is next week is spring break week.
Oh, man.
Yeah, but the bad news is we won't be meeting. So we won't have this class all next week. We will have the class Thursday, hint, hint, but we won't have it next week. which leads me to say that's a great time to get your research papers done. It's also a fabulous time to get your first test done, and maybe even work on your second test. You got a whole week.
You say
Get caught up.
next week, but we're coming.
What's that?
Oh, you mean like this Thursday?
I'm sorry?
This Thursday,
Yeah, we're coming.
No, we have class this Thursday,
Hey, but we're not
but then
coming.
next week, no school at all. Okay.
Man, what?
I don't know. It's just one of these crazy things they do. Okay. No explanation for it. All right. Let's move on to, and by the way, since there aren't any homework exercises unless you want to do them in 2.5, but if you feel like you need some more practice, then in the review exercises on pages 98 and following, you could do, these have answers in the back and also calcchat.com. Any of the odd numbers 1 through 5, 7 or 9, 11 or 13, 15 or 17, any of the odds 19 to 25, 27, 29, 31, 33 or 35, 37, 39, 41, 43, 45, and 47 or 49. After that, you're into the 2.5. You don't need to do those. And they take up most of the rest of the stuff. Okay. So let's move to chapter 3, which is determinants. This is a very short section. It's not going to take us long, and because we've already been doing some of it, that means the third test is going to come up very quickly. So get your papers and first two tests done, because the third test won't be all that long. Okay, determinants. Now, I think we've already done some of this on determinants. I'm certain we have. But let me just say this. Now, they go through this example, so I'm going to do it too, and it's kind of, it's almost time, isn't it?
Just wanted to make sure so you have enough time to just cover.
I mean, aren't we just within a few minutes of ending?
Yes, we got 3 minutes.
How much?
2 minutes.
2 minutes, okay. So I don't even think it's worth starting because I wouldn't be able to get the first example done. So let me change my mark here, and we'll be beginning at this first example. Determinant of a 2x2 matrix, okay? And no new exercises there. So we'll get started on that on Thursday, and it's not going to take us long, I don't think, to get through 3.1. So this is going to go, I think, fairly quickly, okay? All right. So we'll see you Thursday. Okay, good deal.